I move forward to the textile wet processing, talking at first about the woven and knitwear process, and then we'll come to the denim process. So usually in woven knitwear, we have pre-treatment, then we have dyeing and printing, and then we have finishing. And these red processes are the processes which consume energy and water. Others do not consume too much energy, only electrical energy, for example. In this case, we start with shearing, combing, singeing, desizing, scouring and bleaching, or solomatic bleaching. Then we go for washing, mercerizing, drying. Then we use stanter for pre-treatment, and shrinking is controlled there. Then we go to dyeing and printing, where we have dyeing process, which consumes a lot of energy. In printing process, we have curing process, which consumes thermal energy a little bit. In finishing, stanter is the bigger energy consumer, and then we have some chemical treatments, which are listed here, conducted to attain certain finishes or certain types of effects on the fabric. So a general pre-treatment, as we see, starts with singeing, desizing, batching everything together, then post desizing washes. This is for open weights, and then we have scouring, bleaching, washing, dyeing, and if cotton dyeing is required, then we also do mercerizing. I will go into details of each of the process. So singeing is a process where flame is applied in two areas, sometimes in only one area, depending on what kind of finish is required. So direct flame is applied. So fabric roll, if you see the schematic diagram above, the fabric rolls over these big rollers, and the burner burns extra fiber on it, provides luster. So direct flame is applied, and passing fabric over heated copper plates or rollers is also done. So going through the heated rollers, the fabric attains a certain finish. Energy efficiency options here are usually controlling the flame size. If you remember that we did this in the textile company case study as well, that their flame width was more compared to the fabric width. So, and then fabric roll speed can also be controlled if we are going too fast or too slow. If we go too fast, we don't attain the quality. If we go too slow, the fabric gets burn marks. So variable flame width can be explored. It requires a little bit of investment. Burner efficiency, nobody looks at it generally, but if we do a stack analysis, for example, look at the bottom, there was a machine for which we did a stack analysis, and the oxygen quantity was very high. The thing is that if we have too high oxygen, it carries too high flue gas temperature as well, and because the air supply is very quick, so we need to control it. If we control it, control the oxygen quantity and maintain the air fuel ratio, that is where we can improve the flue gas temperature. You can say carbon dioxide is very low and oxygen is very high. So these are some things that we can look at.
How do we control the oxygen and CO2? How do we measure? Is there any sensor, or how to do that?
Stack analysis. Just put a stack analyzer in the exhaust chimney. The singeing machine has an exhaust chimney which throws out air, and this air is taken directly from this burner, which is going, the smoke is going up and the chimney is going out of the factory. So you do a stack analysis there, and you measure the oxygen quantity there and the flue gas temperature as well. That is where we can see if the optimization can be done. And optimization will be done at the burner side, obviously. We'll have to control the air and fuel ratio. Also, it is important to alongside have a look at the fabric quality as well. Sometimes the burner itself is an inefficient one, so it is not really possible to adjust oxygen to a greater extent. In that case, we have to review if the burner needs to be changed, if the blower needs to be changed, for example. And then there is cooling water going in, which goes through these heated copper plates or rollers over which the fabric is rolled over, and these have to be cooled down to maintain temperature as well. This cooling water is clean. It is non-contact cooling water. and it can be directly recovered without any further filtration. So, and it is warm, so it contains some thermal energy as well. And if we have a nearby process which requires hot water, we can feed it there, and then the energy requirement there can also be reduced. Um, and then we have a quenching bath. You can see on the right hand side of the schematic diagram, after the burners, this quenching bath then cools down the fabric, and if we have size applied on this fabric earlier, this quenching bath also serves as a desizing process. So desized and quenched fabric then rolls out here through these drums, which are then draining the moisture as well. So these are the usual options for energy efficiency improvement in singeing. As I said, in desizing process, if singeing is done, then the desizing is conducted in the final bath of the singeing, but this is normally done on denim. Otherwise, desizing is a separate process where we have to do desizing. The desizing can be done using enzymes. So if we have starch-based sizes, then we can use enzymatic process where we need to control the process parameters. Oxidative desizing is very rarely used, which uses hydrogen peroxide or caustic soda. It is very, very rarely used. You can say that it is almost obsolete. Then acids are used if we have synthetic sizes. For example, sulfuric acid or hydrochloric acid can be used. Then we need to have washing after this. For example, especially if we have acids used for desizing, we need to do washing processes to normalize the acids over the fabric and then also clean the fabric. So this washing is a little extensive. That is why you see the machine is a bit longer, which passes through washing and then also passes through at the end drying drums as well. So in drying drums, then we also need to heat up the drums through steam. That is somewhere also where the energy savings can come in from. So usual options here are wastewater heat recovery. So because the washing wastewater is hot, is heated up, and then we can also insulate the hot water baths. We can optimize the process using the pH, temperature, and speed automation. So you need to put 2-3 sensors there. So measure the pH of the bath. If the size is being removed too much or too low, for example, according to that we can reduce the speed, or we can control the temperature parameters as well. If we have a drying process at the end, where we have just like this one, where we have steam rollers, where the steam is going through the rollers and coming out as condensate, this is where we can also install a moisture sensor which measures the moisture of fabric at this end, gives a feedback loop to the steam rollers that the fabric is over dried or under dried, and according to that the fabric rollers can increase the steam intake or reduce the steam intake. Then we have different methods for bleaching. Usually hydrogen peroxide is the most common one being used, but we also have sodium hypochlorite for this is used mainly for chlorine bleach layer. We have sodium chloride, sulfur oxide. So different types are used, but hydrogen peroxide is the most common one which is used usually in bleaching, especially for the non-denim. We have again wastewater heat recovery here, because bleaching process is hot process. A lot of process is heated. The temperatures are usually nearing 100 degrees Celsius, sometimes above that. So the wastewater that goes out, big potential of recovering heat from there. But the main issue would be the pH and the content of hydrogen chloride or bleaching agents in the wastewater. So we might need to consider the material of the heat exchanger in this case. And usually the payback is around 6 months to 1 year. Then we can also improve the heat exchanger material inside. For example, if we have mild steel or other kind of ferrous materials, we can consider switching to stainless steel, which provides quicker heat exchange and has longer life. It also reduces corrosion, so and also improves heat exchanger efficiency. So consider doing that. Also, one issue that we see often is that heat exchangers of these machines are leaking, where we have too high or too low pH, or the clogging also takes place. The stainless steel heat exchangers provide a lot of protection against that. So a lot of maintenance cost also reduces here. So massaging process is a refining process which improves tensile strength, provides dimensional stability, and also improves absorbency of the dyeing process. So for this we use sodium hydrochloride bath usually, with heat treatment under tension or sometimes without tension as well. After the sodium hydrochloride treatment in hot bath usually, then we do neutralization using an acid, and then we do washing processes. If you see the schematic diagram in the bottom, you will see that it's that on the left hand side is an entry device, and then it goes through different processes. We have at the end a drying process as well, this vertical tower, which then dries the fabric before it leaves this process. And again, these drums usually are heated up by steam. So steam goes in and comes out as a condensate. And these in older machines there's no control. You can either switch on the steam or switch off the steam. But if we have a moisture sensor again at the end of these drum rollers or in the middle of the processes, we can optimize, give a feedback loop to the solenoid valves of the steam drum rollers, and then we can control the steam intake as well. If we control the steam intake, we can reduce significant amount of steam intake. So there is one vendor which is supplying these equipment, importing this from Germany, from Europe, supplying this equipment in Pakistan, and it has been claiming 14% steam savings. Obviously, the calculations I have seen, the factories say that they don't have steam flow meters here, but their feeling is that it is saving more than 14% of the steam. But there are no actual calculations being done generally. This is being installed everywhere. Best thing about it is that it provides process control and quality control, and along with that obviously then provides savings as well. So this is something to be looked at. Ammonia is used very rarely in mercerizing process, but this is also used in some areas. Then if we are using sodium hydrochloride, what happens is that we have a strong sodium hydrochloride solution that goes in, which has high strength, and then after doing the mercerizing process, it comes out as a weak sodium hydroxide solution. Some factories drain it, it goes to the effluent treatment plant, and then you need to normalize this using acids in the ETP. Some factories just put it back into in the first bath, this reroute it into the first bath so that they use some of this solution. But the best way is to recover the caustic using a caustic recovery plant. There is another way that the mercerizing wastewater can be reused in scouring process. And then if you don't have a caustic recovery plant, so it can be used in the scouring process as well. So do look at these inter-process reuses, which actually saves energy as well as reduces water consumption. I can show you one case study that was done by IFC, that this one factory actually installed a caustic recovery plant where the weak caustic from mercerizing unit is coming in. There is steam also applied to this process and cooling water is going into this process. We have recovered caustic back to the mercerizers. We have vapor condensate out. That also goes to the mercerizers collected from top. Hot water and steam condensate goes back to the boiler and wet processing units depending on where it can be used. And so they are able to use sodium hydroxide, able to recover 24 to 30 bume, which is quite high strength. And H2SO4 consumption is also reduced at ETP, where they had to normalize this alkaline solution. And then hot water is available to be fed to the processes, saving a lot of steam as well. Calculating all these savings, the return on investment is less than 3 years in this case. Then once this pre-treatment is done, we come out of it, and then the material has to be dyed. Dyeing is done on twin yarn. So twine is when the cones are dyed. Then we have yarn dyeing, where the open yarn is dyed for the denim process, for example. Fabric dyeing and garment dyeing is also done. All these processes can be divided into two type of processes. One is batch process and one is continuous process. Continuous process is the one where we keep on feeding fabric from one end in form of rollers, and on the other end the fabric keeps coming out. So these processes are normally done on longer machines, where we have the dyeing process, and then we have the washing process, and at the end we have the drying process as well. Usual techniques are gel dyeing is used for artificial fibers. Pigment dyeing can be used with binders, also not used very commonly for cotton. Diffusion dyeing, exhaust dyeing, ozone dyeing, there are different methods done. Ozone can be used on indigo or black sulfur fabric. And if we are using ozone machines, there's upfront investment required in ozone machine, in ozone generator, and also safety training of workers also needed, because with ozone we also get some health and safety hazards as well. There is also cellulose fabric dyeing, where we need reactive dyes. The temperatures are around 65 degrees Celsius, and machines work at atmospheric pressures. Synthetic fabric or blended, the dispersed dyes are used normally here. The temperatures are above 100 degrees Celsius, and the machines also need to be pressurized in this case. Then we have these discontinuous dyes, where we have different kind of machines. I will show you going forward. We have semi-continuous as well as continuous dyes. Usually, first step is a coloring agent is dissolved in a dye liquor. Dye stuff then diffuses into the liquor, and then we have a dye bath. And then through a certain process, either batching process or a continuous process, dye stuff accumulates on the surface of the yarn or fabric. It depends on the quality of the dye stuff, the affinity of dye stuff, fixation rate of the dye stuff, for example. Then it comes to the penetration. So the dye has to be provided enough time that it penetrates the fiber of the yarn or the of the rope or of whatever material we are dyeing. So it is important that that it has the absorbency available. That is why then we are doing the mercerizing process earlier as well. Sometimes salt has to be added to overcome the electrostatic surface barriers here. This process needs heating, normally over 100 degrees Celsius, but also depends on what kind of material we're dyeing, ranging from 65 to 70 degrees, going up to 130 degrees as well sometimes. And then fixation of dyes is required, where the further heat is provided. Some auxiliary chemicals are added here to improve the fixation of dyes. And if we have high fixation dyes, we might need less heat here, and we might need less number of baths here as well. There are two common main factors that have to be kept in mind when we're looking at the dyeing process. One is the liquor ratio, and second is the fixation rate. So liquor ratio is the ratio of quantity of fabric to the dye bath liquor. So kg of fabric into the kg or liters of the liquor or the dye bath that we have prepared. Our aim is to achieve low liquor ratios. For example, if we have 200 kg of fabric and we have 1400 liter of dye bath, and we have a liquor ratio of 1:7. And then we come to the fixation rate. That is the percentage of dye used that remains on the material to be dyed. So if we are, for example, feeding in uh, 10 kg of dye, and 70 kg of the dye goes into the wastewater and 30 kg remains on the fabric, then we have a fixation rate of 30%. And different extraction or fixation rates are there depending on what kind of process we are using, how much heat we are using, different kind of chemicals or dyes that are being used. So fixation rates vary. So we have different kind of batch dyeing machines. We have bobbin dyeing. This is the process that Donato was discussing last time, where we have these bobbins or cones stacked into the machines, and there is water going from inside out or outside in. And we have in the bobbin dyeing usually the bath to one bath to the cone or the yarn ratio is 1:8 to 1:15. If we have hank dyeing, then we have 1:12 or 1:24 liquor ratio. So this is a process which is used for fabric dyeing. So on the left hand side we have beam dyeing, where we load the beam roller into the machine, and it is dyed while the beam is static, and the dye is pumped. On the right hand side we have a jig dyeing, where the beam is loaded and the fabric unrolls on the beam and then the re-rolls on the second beam. It goes through a static bath of dye. So on the left hand side we have static beam and the dye is moving. On the right hand side we have a static dye bath and the fabric is moving. The liquor ratio of the jig dyeing is 1:3 to 1:6. It's good liquor ratio. Beam dyeing on the left hand side has a little bit higher liquor ratio. All these processes, this process again, as explained earlier, needs electricity and also needs steam for heating up the process or the dyeing bath. Then we have winches. These are most commonly used in knitwear, especially where we have these this dye baths in the middle, and then we have this fabric, which is this knitted fabric tube, which goes through this. For example, this winch has 3 openings here to see how it is going, and then we can load multiple rolls here. They go through the bath. Outside the machine is the loading and unloading reel, and so it goes through the dyeing bath and comes out. So that is how the fabric keeps on rotating. The fabric is loose inside the dye bath, so there's high tension on the top where it is on the fabric, where is it on the rollers. The fabric is on the rollers. In the bottom, in the dye bath, the fabric is loose. It is provided enough time to stay inside the dye bath to be dyed. The liquor ratio here is also very high, 1:15 to 1:40 liquor ratio. Then we have jet dyeing, pretty similar to winch dyeing, but in this one we can have many knitted tubes that we can put in. Liquor ratio is much better than the winch dyeing in this case. These are also called soft flow machines. You can see in the bottom, the flow of fabric is very soft. It is provided even more time compared to winch dyeing. Again, it includes heating process, it includes cooling process. So these batch machines, all these batch machines that we're talking about, they have multiple processes inside one machine. So first of all, you would prepare a dye bath. You will heat up the dye bath. So it takes time in heating up the dye bath. Once dye bath is heated up, then you start the dyeing process. Once it is done, the leftover wastewater is released. Then you load again washing water, and the rinsing is done. And then you do hot water washing, and then you do cold water washing. So there's a lot of rinsing and washing and cooling done here, and then the fabric comes out. So this is what is done in all of these. But the fabric that comes out of these machines is wet. There is no process of drying the fabric inside these machines. So there are no dryers. It's all wet process. Some baths are cold, some baths are warm. And for each warm bath, you have to wait for the process to heat up to a certain degree Celsius, and then you can start rolling the fabric. So this is one drawback of these batch machines. The wastewater that comes out In older machines, hot bath, cold bath, all the baths would be drained from the same wastewater channel. But there are new machines coming up, or even as Donato last time also explained, that you can also put sensors with the wastewater that is going out. Put sensors if it is a cold wastewater going out, it redirects to a certain cold wastewater drain. If it is hot wastewater going out, it redirects to the hot wastewater drain, and then we can do a wastewater heat recovery there as well. I have put together only commonly used machines, so that, I mean, the process generally is same. It's just that with the changing technology, the liquor ratio is improving. You can load multiple fabric tubes on it, for example, if it is knitted, or and you can, have better control of the process with new machines. That is only what is improving with it. Then we have these feed through dyeing machines, which are continuous dyeing machines. You can see on the left hand side, the fabric is entered in the schematic diagram. It goes to the dye pad, then it passes through the air, where we provided enough time to fix to do the fixation. Then it goes to the infrared, where we do some electrical flux. So then we have the hot bath, we have chemical pad to improve the fixation. Then in the steaming, this is a process where we apply steam to the fabric, and then to the rollers. And then we have this rinsing, oxidation, soaping, rinsing, neutralizing processes. All these processes are done for the dyeing machines. In these machines, the biggest usually possibility is to provide a counterflow. So usually this dyeing process is not only one pad. Sometimes we have multiple dye baths. 7 to 8 dye baths are there. So what we can do is we instead of entering fresh water in the first dye bath, we can enter fresh water in the last dye bath, and then this water flows from last dye bath towards first dye bath using gravity or using pumps. So always the water is entered in the last dye bath, and exited from the first dye bath. Through this way, we can save the water quantity, chemical quantity, as well as heat required for the dyeing process. That is called counterflow dyeing. So energy efficiency options in dyeing machines generally is, for example, if we use low TDS means total dissolved solids. If we use water with low TDS for dyeing as well as post dyeing operations, we can reduce the quantity of dyes, chemicals, and auxiliaries. We can reduce the process time. We can reduce the heat required for fixation processes as well. And we can also reduce the liquor ratio. And with the reduction of liquor ratio comes the big benefit of reducing the energy required, electrical as well as thermal energy required. Because if you ever have you, but in areas where water quality is bad, if you go there, let's talk about residential water supplies. If you go to areas where water quality is bad, and you try to wash your hands or wash your face or even wash your clothes, you need to apply more soap, because hard water has low absorbency in it, so it cannot absorb a lot of other things, because it already has high total dissolved solids. So it needs more soap to take in for washing process. So if the soap sticks to your hand, you're trying to wash it, and the soap is not coming off very quickly. But if you wash your hands with normal good quality water, or normal drinking quality water, the soap comes off pretty quickly. So same is the problem with the dyeing process as well, dyeing as well as washing process. If the total dissolved solid quantity is high, then you need more chemicals. If it is low, then you need less chemicals. So best practice is to use reverse osmosis water for the dyeing process, where the dyes get absorbed in the water very, very quickly. So you need less time for absorbency, you need less time for the dyeing process as well, and hence the less liquor ratio as well. Then improving heat exchanger material. So inside these machines, steam is going in, it goes through heat exchangers, heats up the dye bath, and comes out as the condensate. So these again, as discussed earlier, you can improve the heat exchanger material, go towards aluminium or copper or stainless steel. These are expensive ones, but they provide good heat exchange and also have very less incidents of leakages or corrosion. Then low liquor ratio and use of high fixation dyes. So if we are using high fixation dyes, these dyes normally fix very quickly. So we need less number of baths. I've seen often that the number of dyeing baths and number of washing baths have reduced to 50% if the high fixation dyes are applied, especially in denim process where rope is being dyed. High fixation dyes has cut down water input by 50% in dyeing process and in washing process. And consequently, it means 50% less energy consumption and 50% less process time as well. Then improve insulation of machines. As you can see on the right hand side, I did a thermal image of this one machine, and you can see that there are many areas of the machine which are at 120, 130 degrees Celsius. This is temperature leaking. So this is heat dissipating from the machines. So improving this insulation. So machine insulation is more expensive compared to insulating the steam lines or valves, but it does bring fruits, but it also improves the health and safety, improves the environmental temperature. So if we have covered these, there are other benefits which are indirect. For example, we need less cooling or less ventilation now. There will be less accidents because of reduction of contact with the hot surfaces, for example. Then big point is wastewater heat recovery. If we have a continuous machine like this one, wastewater heat recovery is quite easy. If we have this kind of batch machines, it is a little bit critical, little bit difficult, but this was discussed already in detail last time, so I won't go into detail of this. We already have discussed cooling water recovery and reuse for singeing as well, which is also easily applicable in these processes as well. Usually the cooling here is applied in these continuous machines. The cooling is applied in the process continuously. In some areas where cooling is required, however, in these kind of batch machines, cooling water enters into the machine after the process is completed. So they have to cool down the machine, and then they can so that they can prepare the machine for the next batch to be loaded. This cooling water can be recovered. Then there is washing water as well. So once we have completed one process, then we actually wash the machine from inside. So the first washing that we do without fabric, so the machine is loaded with water and washed without fabric. This first wash is not recoverable, but then we do another wash, and this water is usually clean and can be used again in the next bath as well, but we need to have a washing water recovery unit as well for in that case. Then switching to cold pad batch. This is a new technology, emerging technology. It reduces energy and water consumption by 50%. It does not require salt, hence reducing the pollution load. And there's no abrasion required on the fabric, so the dyed fabric has smoother surfaces as well. But obviously not every process can be switched to cold pad batch dyeing. Not every reactive dyeing setup can be converted. So there are some limitations. Obviously, one has to look towards those limitations as well. As you can see that my first line of this slide says that it is not possible to switch to CPB for all of the all kind of dyeing processes. Number one, it is to only reactive dyeing can be done on this. Non-reactive dyeing cannot be done on this. So this is very important because we're not heating up the dye baths to 65, 70 or 80 degrees Celsius, but rather we're doing the dyeing process at around 50 to 55 degrees Celsius in most of the cases. So It is important to know that we cannot shift all of these, but we can only shift reactive dyeing, but obviously not all of those. As you also said that a high precision and control is required, the process is slower. So I do not recommend that the factories totally shift on cold pad batch dyeing. This can only be done on batch dyeing, as you can see from the name. The continuous dyeing machines cannot be shifted, so only the batch dyeing machines can be shifted. The best way is to go for a machine that allows for using cold pad batch for a newer technology rather than converting the older technology machines. But never just recommend factories to shift to cold pad batch dyeing. Cold pad batch dyeing here is only shared as an information that this is one of the processes. It is very important to look at the process quality parameters. And when we are shifting on cold pad batch dyeing, it is recommended that we share with the machine supplier or the process modifier the quality requirements, the type of chemicals we're using, the quality parameters, functionality parameters of the fabric. We provide this information to the machine supplier, and then we do a detailed discussion on the technical feasibility of this process, because this is not very easy to do, and you need also more skilled workers and more precise automated controls here. And also being energy auditors, and if we don't understand the process parameters as such, my recommendation would be, rather than asking the factories to shift to it, ask them if they have ever considered shifting to cold pad batch dyeing, and what are their opinions about it, and which of the processes, which of the fabrics they think can be shifted. So rather than suggesting, I would say put it into an inquiry phase, so that we have a discussion around it rather than putting it as a recommendation. So far, I have never put it as a recommendation to any factory.